Have you ever stopped to wonder how your phone can find one specific contact out of thousands in like a split second? Or how a website checks your password almost instantly? Well, the secret behind so much of that incredible speed is a really clever idea called a hash table. So let's dive in and unpack this amazing piece of technology.
Right, so how do they pull it off? How can a massive system find the exact piece of information you need, seemingly out of nowhere, with basically zero delay? That's the puzzle we're going to piece together in this explainer. To really get the solution, we've got to understand the problem first. And at its core, it's all about one thing: speed. We need a way to store tons of information and then look it up, crazy fast. So, the basic tool for this job is something called a map, or maybe you've heard it called a dictionary. In computer science, they call it an abstract data type, which is just a fancy way of saying it's a blueprint for how data gets stored. The idea itself is super simple but really powerful. You take a unique key and you link it to a value. So, for example, the key 48 could point to the name May. You give the map the key and bam, it gives you the value right back. Sounds easy, right? But the real trick is, how do we build it to be fast? Okay, so let's start with the most obvious idea you could possibly think of. What if we just use the keys themselves as the address or the index in a simple list? Now, if you look at this, the real beauty here is the speed. If you want to find the value for key number 7, you just go straight to position 7 in the array. Boom, done. This is what we call an O of 1, or constant time operation, and that's a huge deal. It doesn't matter if the list has 10 atoms or 10 million. It takes the exact same single step to find what you're looking for. This is pretty much the gold standard for speed.
Ah, but you knew there was a catch, right? This simple, brilliant idea completely falls apart in the real world. I mean, what if your key isn't a number at all, but a name, like May? And even if it is a number, what if it's gigantic? A standard integer can be over 2 billion. You literally can't create a list with 2 billion empty spaces just in case. It's not practical at all. Okay, so what we need is a way to get that incredible array index speed, but without the insane memory waste, and without being stuck using only little numbers for our keys. So what's the solution? Enter hashing. And the heart of this whole thing is the hash function. I want you to think of it like a magic machine. You can toss anything into it, a name, a huge number, whatever, and it crunches it all down and spits out one single manageable number. We call that number a hash code. It's the magic trick that turns any kind of key into a useful number. You can see here, the whole process is really just 2 simple steps. First, you run your key through that magic hash function to get the hash code. Second, you use the modulo operator, that's the percent sign, to shrink that hash code down so it fits perfectly as an index within your array. And that's it. That 2-step recipe is the core engine of a hash table. All right, let's look at a real example so you can see it work. Imagine we have an array with 10 slots, or buckets. If our key is 86, we get its hash code, and then we calculate 86 modulo 10, which gives us 6. So the data for key 86 goes right into bucket number 6. Same thing for 23, it lands in bucket 3, and 42 goes to bucket 2. It's a predictable, repeatable, and seriously fast way to find the right home for any key. So this seems perfect, right? We've designed this beautiful, elegant system. But there is one little problem that's pretty much guaranteed to happen. What happens when 2 totally different keys try to land in the exact same bucket? Yep, this is called a collision. It's what happens when our hashing process, just by random chance, points 2 different keys to the very same spot in our array. And since each bucket is only designed to hold one thing, well, we've got a problem. So let's make this super clear. A minute ago, we put the item with key 86 into bucket number 6, but now a new item comes along with key 16. Well, guess what? 16 modulo 10 is also 6. We try to go to bucket 6, but it's already taken. We have a collision. So it's really important to get this. Collisions aren't some weird fluke. They are an inevitable part of hashing. It's just what happens when you try to map a huge, nearly infinite world of keys into a small, finite number of buckets. The good news is, engineers have come up with some really clever ways to deal with them. The 2 most popular solutions are called chaining and linear probing. You can think of it like this. Chaining says, hey, let's just create a little waiting list inside each bucket. Linear probing is more like, if my spot is taken, no big deal, I'll just check next door. Let's look at how they work. Okay, so chaining is a pretty intuitive idea.
Instead of a bucket holding just one item, think of it as holding the start of a list. When a new item hashes to that bucket, you don't have a problem. You just add it to that bucket's own private little list. And this visualizes it perfectly. Let's say both the key 77 and the key 49 happen to hash to bucket 0. No problem at all. Bucket 0 now just points to a lift that contains both of those items. So to find something, you just zip to the right bucket and do a quick scan of its tiny list. Easy. Now, the other big strategy is called linear probing, and this one's even simpler. If you hash to a bucket and find someone's already parked there, you just probe or, check the very next bucket. If that one's open, great, you take it. If not, you just check the next one and the next one until you find a free spot. You can see it right here. Key 77 hashes to bucket 0 and grabs it. Then key 49 comes along and also hashes to bucket 0, but it's full. So the linear probing algorithm just says, okay, let's look next door at bucket 1. Hey, it's empty. So item 49 gets placed there instead. Problem solved. So we've gone from the problem to the solution and even figured out fixes for its main weakness. But why does any of this matter? Well, because this data structure is, and I'm not exaggerating here, one of the absolute foundational building blocks of our entire digital world. Seriously, if you've ever used a dictionary in Python, you've used a hash table. They are the reason database queries are so fast. They power the caches that make your web browser and your computer's processor feel so snappy. They're just everywhere, working silently in the background to make sure your digital life moves at the speed of thought. And that's really the whole story, isn't it? It all started with a simple need. How do we find stuff fast? And from that, this incredibly powerful, elegant solution, the hash table, was born. It's this perfect balance of speed and practicality, and it truly does underpin so much of the tech we rely on. So I'll leave you with this thought. Now that you know the secret ingredient, think about all those instant interactions you have with technology every single day. How many of them, from your social media feed to your Google searches, are really just powered by this one simple, incredibly clever idea of hashing? It's kind of amazing when you think about it.